Merhabalar. Hi. Sorry, I said it in Turkish first, so let me switch to English language. So what we have done already is Boolean algebra. We introduce you what Boolean algebra is. That's pure mathematics. And then we are transferring this mathematics to applications. We could use this Boolean algebra in propositional algebra. You might call it language as well. And the other one is logic circuits. So we will be explaining this frame now. And then in this frame, basically we are going to see the logic elements and the Boolean algebra relation, and then Boolean algebra and logic circuits relation. So let's go into this. What we have here. Let me click here. Go in a bit. In Boolean algebra, we defined our algebra in the set on the set of S, which includes 0 and 1 only. That means all the functions that we can define on this set is going to be a Boolean function. That means formula form functions. All of them is going to be like that, Boolean function. And we will be dealing with only the algebra where S set has got 2 elements only. That's why we call it binary logic circuits that we're going to see. Binary, 0, 1, 2 of them. That's why we call it binary. So in Boolean algebra, we've got 2 array operations, product and sum operations, and 1 array operation, complement. These are basic operations. There are basic fundamental elements which corresponds to these theoretical operations in practice. These are AND, OR gates, and NOT gate. So, for example, this one here, it is shown, AND gate is shown like that, OR gate shown like that, and NOT gate, or the complement, or the inverter is shown like this. So definition relation, if the inputs are known, the outputs are known. So since we've got 2 inputs here, permutations of 2 symbols in the form of 2, there are 4 alternatives, 0, 0, 0, 1, 1, 1, 1, 0. So that means 2 to the power 2, isn't it? 2 symbols, permutations that you can find out is just 4, 2 to the power 2, which is equal to 4. So for these 4 inputs, what is the output is given here. So you can call this a definition relation, and you can show it x times y. So we know the first time, second type of expansion that you can write it. So for that one, for example, this is the true mean term. The corresponding product term is x times y. So that's the formula for it. So that's the definition relation. So similarly for the AND gate, so it's going to be, if you consider the second expansion, so you're going to make it x plus 0, y is plus y. Why is that? Because the corresponding true max term, this variable has got the 0 value. The corresponding term in this is going to be plus, isn't it? The opposite of the first expansion case. So x plus y is the output of for this input is given here, and as a formula is this. This is the logic function, Boolean function corresponding to this element, and this is the logic function corresponding to this product element or the AND gate. The complement, so it is that you don't need 4 lines here. Can I write here? No, you cannot write now. 4 lines is just 2 of them is enough, because since you've got 1 input here, it could be 0. When it is input is 0, output is 1. When input is 1, output is 0. So just writing 2 lines, I could have represent this NOT gate. Now we need to explain one thing here. In these definition relations, as you know, there is no time here. But we know that all the variables, electrical signals depends on time. So where is time? Time is embedded in. How it is embedded? So you can go. So these 4 lines tells me the number of inputs, different inputs that you could apply to these gates. The number of different inputs that you can apply is 0, 0, 0, 1, 1, 0, 1, 1, just 4 of them. But in practice, we are applying these inputs as bit streams. So how it is bit stream? For example, this is the bit stream for variable x, and this is another bit stream for variable y. So if you consider both of them together as the input of the AND gate, so it's going to be 0, 0, the first input come in, so that means time interval, this time interval. For the time interval, your output is 0. In here, as you see here, this time interval 1, 0, that means your input 1, 0 is not changing, so your output is 0, as you see here. So for different time intervals, for each input, separate input, we have a time interval. So for this time interval, we've got the output value. So time is included here. So you see here, you can consider time is changing that way. So this bit stream tells me the bit stream of x, and this time shows you bit stream of y, while how it is changing as time progresses, isn't it? So you're getting the outputs here. So time is here, you see. So in order to include the time, we are talking about bit stream, as we said here, streams, or input sequence. From time to time, you might call it input sequence as well. So input sequence is the combination of the inputs that we see in the definition relations of the different inputs. In here, we could see these inputs in the stream in any order, because these are independent variables. So I might see this input and then this input and then this input. It could be any order, and any input could be repeated anytime you like. So by using this any order, any input, any repeated time means you set a bit stream, input bit stream. So for each bit stream, input bit stream, you can tell the output bit stream just by using this definition relation. So we don't use these bit streams in the definition relation. We only use the different inputs that we could apply to the input of a 2-input AND or gate. So we've got to know what bits the relation between the different inputs and the bit streams. So these are the fundamental operations in Boolean algebra and the corresponding gates in practice. But in practice, we have not only these basic components, we've got some other components as well. These are NAND gates, NOR gates, XOR gates, and XNOR gates. These four of them, once again, has got 2 inputs, and the definition relations are given here. For the NAND gates, you can consider that there is an AND gate, and output is connected to the input of a NOT gate like that, and then get the output. So what you get is AND is x times y. It is a product term. The prime of it, not of it, or the complement of it is going to be this one, isn't it? According to there was a theorem we said for that. I can't remember it now. So you can get x prime. This is equal x prime plus y prime, isn't it? De Morgan theorem that we got here. So you can write this function in different forms as well. That is the definition relation as the truth table. That is the formula related to that. When you come to the NOR element is the OR element, and the output connected to a NOT element gives you a NOR element. So we don't make this NOR element by using two elements together. This is just one element, and it is shown like that. Not NOR element, OR element, a small circle at the output. We show it as a NOR element. Exclusive OR gate. So definition relation in here. So I can tell you a rule how to remember this element. If the inputs are different, has got different values from each other, let's say 0, 1 and 1, 1, your output is 1. If your inputs have got the same value, 0, 0 or 1, your output is 0. So by just looking at the output, you can say what the inputs could be. If the output is 0, that means input values are the same. That means it could be 0, 0 or 1, 1. If your output is 1, so your input, it could be either 0, 1 or 1, 0. That means different values. So from this definition, if you use the first canonical expansion, you get that formula. So we can show it by this symbol here, a circle inside a summation operation to represent exclusive OR. If there is a NOT gate connected to the output of an XOR gate, it becomes XNOR gate. XNOR gate definition relation is the complement of this. So complement of this gives you this. So you could do it at home, how you could get this. Or you might consider the first canonical expansion of here, and you get this. Exclusive NOR gate. So 3 gates that we see in here, another 4 here, altogether 7 gates we've got available in the market. These are not the basic operations, so I can represent each. These are Boolean functions. I can represent any element that you gave us as a Boolean formula like that. I can represent the same thing as a truth table as well, of course. So when you look at in general, so we have seen up to now only the 2 inputs included at most, and then all these gates have got 2 inputs. But in practice, there are more inputs included circuits. So these are the examples. This is a 3-input AND gate. This is a 3-input NOR gate. This is 3-input NAND gate. This is 3-input XOR gate. This is 4-input OR gate. These inputs, it could change different numbers. It could be 10 inputs, 7 inputs, all of them for all these types. It is possible. So you can write the formula easily. If it is AND, you're going to multiply all these inputs. If it is OR gate, you're going to add them up. So if it is not, so you're going to get the complement of the output. Fan-in, I've got to, this is a new terminology for you maybe. This is fan-in. Fan-in is the number of inputs to a gate is called fan-in. So for example, fan-in is 3 here, 4 here, 3 here, 3 here, 3 here, 2 here, 2 here, 2 here, 1 here, fan-in. So the next frame is related with the commercial gate packages. These elements that we have seen up to now, they are not sold in the market separately. They normally put 4 of them in one package. It is called integrated circuits. So in one commercially available integrated circuit, we've got 4 AND gates, 2 input AND gates, 4 of them in one integrated circuit. So 2 input, 1 output. For each AND gate, I've got 3 terminals. So when it's 4 terminals, 4 gates here, that means 12 terminals. But in the integrated circuit, we've got 14 terminals. Why we add those 2 additional terminals? In order to run the transistors in linear region. So in this gates, if I go in a bit detail, in this gates, we've got inside we've got transistors. How we got the transistor to get this element is a separate subject. It's not related to this course subject. So inside there are transistors. So in order to run this transistor in linear region, we've got to apply DC sources. So this DC source comes from that VCC and ground. So these are required in order to run this transistor inside the AND gates. So this DC input should be applied externally. It's not inside, so it is going to be externally applied. So in the lab, you're going to use 5-volt DC sources to be connected to these two terminals. So there are different technologies to produce these integrated circuits. It is TTL logic is one technology, CMOS logic is another technology, and some other technologies are available. But the boolean algebra application, the logic circuits that we deal with in theory here in logic design course is independent from these technologies. Whatever the technology is, the definition relation that we use in here is not going to change. But in the lab, I can tell you, we're going to use TTL logic, and the power that you're going to apply to this VCC and ground is going to be 5 volts and 0 connection to those. So one more thing that we should talk about, if the integrated circuit has got at most 10 gates in it, it is called single scale integrated circuit. If it has got gates up to 100 gates, then it's called medium scale integrated circuits. If it has got up to 10,000 gates, it is called large scale integrated circuit. If the gates is more than 1,000, it is called very large scale integrated circuit. We are going to see some of these, not VLSI, but SSI, MSI, and LSI integrated circuits in this course. VLSI, the example for this VLSI is microcontroller type of elements. So we are not going to see in this course. This is going to be microprocessors as a separate course. So finally, I've got to mention one more thing here. So we've got zeros and ones in theory. How we are going to represent these zeros and ones in practice? So electrically, we've got two variables. We've got current and voltage. So we can represent this theoretical 0 and 1 by current and voltage. When the voltage is 0, is logic 0. If voltage is different from 0, then we can represent 1. So if you're going to use voltage, we call it voltage logic. You could do the same 0, 1 representation by using current, so it becomes the current logic. The alternative is this positive and negative logic. Positive logic, if the higher the value of your physical quantity, let's say voltage, higher the voltage, represent 1, lower the voltage, represent 0, it's called positive logic. If it is opposite, that means minus voltage represent 1, 0 represents 0, it is called negative logic. It is true for the current and voltages. Therefore, totally we've got 8 alternatives, isn't it? One of them is positive current, negative current, positive voltage, negative voltage logics. There are altogether 8 of them. Not 8, 4 of them. But we're going to use in the lab, what we're going to use is the voltage logic, and it will be positive logic. That means when the voltage is 5 volt, in theory you are representing 1. If your voltage is 0, then your theoretical value is 0. So we mentioned about the fan in, let's call about fan out as well. Fan out tells us how many connection you could make between this element output and the other element's input. So for each element, fan out tells you how many different inputs you can connect this element output is the fan out. If it is fan out 10 means for an AND gate, this AND gate output can be connected to 10 different logic elements inputs. That tells you fan out. Why we've got a fan out concept, I will explain these in different frames later on. So that's the end of this video then. Let's escape from here and stop.